All right, today we are going to talk about the four-color theorem. So a little bit of background so it makes a little bit more sense. Essentially, the four-color theorem started because there's this guy, Guthrie, in 1852, that whenever he was looking over a map of the English counties, as you can see over here on the right-hand side of the screen, he noticed that it only needed four colors, and he thought to himself, "That's interesting. I wonder if this would always hold true." And so he asked his brother, who at the time was um, studying math. Guthrie, who at the time was gearing up to become a lawyer, so of course he had to outsource his questions. Um, and then a few years later, um, there starts to come out proofs, and more proofs come out. The first proof that was very well known was by Kemble, and this was later shown to be false 11 years later. And likewise, there were plenty of more proofs that came about that were um, proven incorrect, and that was for a multitude of reasons. But that sort of continued to occur until 1976, when two English mathematicians yet again prove the four-color theorem um, using computers, and we'll sort of get into that more in a little bit. But that's just sort of like the general outline for what they were doing. So this is all sort of contextual. You could also think of it in a more general form. If you look at, like, say you're looking at a map of the United States, this theorem will continue to hold true. So that's just sort of the general outline. Now we can get into the specifics. Um, so as I mentioned, this problem was left unsolved for over 100 years. So how did eventually this all come about? Well, there was this thing called the five-color theorem. Remember the five-color theorem? If you don't remember it, I'll give you a little reminder of it. The five-color theorem says that given a plane separated into regions, the regions may be colored by no more than five colors, and two adjacent regions get the same color. So remember, all that means is that you're not going to have points connected that are going to be the same color. So that was known to be true, but with that being said, it was no more than five colors. So what if you wanted to have less than five colors? How could you make this true? As in a general case, obviously you could make this true in individual cases. You could have one color, you could have two color, but they wanted to see if Guthrie's initial question was, I've noticed that there are only four colors for this map. I want to make this true for a general case, since that was a specific case. So what eventually, as I said, remember there were lots and lots of proofs. Typically, as it goes in math and sciences, really, you build on things. So it's not that every single proof was completely wrong. Some mathematicians had very great ideas. They just fell short in other ways. So we all sort of build up to this grand idea of how we can solve this great unsolved mystery, as I put it. Maybe not so great, but a mystery nonetheless. So what mathematicians decided to do was, we have five colors. So what if we just start taking off a color? What if we, as I've mentioned here, reduce? We just take away a vertex, or one vertex, until we go from n plus one amount of vertices, and we bring it down so that instead of having our five colors, we only have four colors. Then that would hold up that we would show that the four-color theorem, as Guthrie first presented it, would be correct. And is this fair? Yes, of course, this is fair. All you would have to do is, say for this graph down here that we have A, B, C, D, and E, all we would do is, say, take away E, and I guess this is maybe not the best of examples, but you can see that A, which is red, is not going to touch any of the other colors. This is obviously a very reduced graph, but I think you can get the point from there. The idea is that you just have to make sure that you can always take away and reduce your graphs until you have just your four colors. Okay, so I hope that made sense. But as I mentioned, of course, Guthrie had his individual case, but he needed it to be generalized. Okay, as you do in math, you can always find a case of something being correct. But that doesn't necessarily mean that it's true. Sometimes you can just get lucky. Sometimes it just happens chance. So does this work for every graph? And that became an issue, and that's the reason why it took over 100 years to figure out. It was unknown for a very, very long time until, as I mentioned, these guys come around. They actually begin their work in 1972. Apel and Haken. Again, we have some British guys coming up to solve a British problem. They decided that they were going to use this newfound technology. They were using computers. Computers had been around for about 30 years, maybe a little bit more whenever they, a little bit less, sorry, whenever they came about it. But they figured that there were 2,000 different configurations, 2,000 plus really, of these different configurations and how to reduce them. But of course, they had already spent. I mentioned that they started in 1972, so that means that they had already spent 4 years coming up with these configurations. They didn't want to work through these; they were already worn out. That would just be impossible. That would take forever. So they put together these set of rules, almost like if you were a computer scientist. I'm not a computer scientist, so I don't know exactly how it would have worked, but this set of rules so that they could reduce their 5 colorable graphs and create them into these 4 colorable graphs, and in essence proving the 4-color theorem. And alas, they were able to do that. That's why we learned about the 4-color theorem in class. And this was a great win for map creators of the world, and everybody rejoiced, and it was a very happy day in England. And everybody knew that you can use 4 colors to create these graphs. And of course, since it is kind of a very random example, you'd always think that somebody doing a final project on it, of course, there has to be some big reason behind it. And the big reason behind this, why this proof is important, is because of the implications. As I said, this is relatively new technology. Computers haven't been around for too much longer, so it was impossible for some of these, maybe I don't want to say ancient, but some of these older ideas to maybe be proven. Maybe they were thought to be true, but they couldn't necessarily be proven because you didn't have something like a computer that could go and configure these 2,000 plus results. But as everything does, there are always their skeptics. Some people argued that what's the point of just getting an answer if you what's the point of getting the answer if you don't really know the route to do it? This is just some computer spitting it out an answer. However, in the long run, we see that this is sort of a new era for math, that computers are able to help us and be at our side. I put right here an example. Remember a few weeks ago in class, whenever we were doing, I think it was an in-class assignment, we were learning about stationary distribution. We didn't want to go through and find the stationary distribution, so we used technology. We used Wolfram Alpha. I think that's what I used. I think there were a few other things that Professor Sullivan allowed us to use, but that is a great implication of sort of this maybe mundane, you could say, idea about the 4-color theorem, but it ended up being huge that we could use computers to now prove these mathematical theories. So that is all I have to say about the 4-color theorem, and thank you for listening.